Hello everybody. In this video we move on to differentiability. This is a topic I'm sure you covered way back in your Calculus 1 course, and the definition we give is not going to be terribly different from what you saw there. It's not going to be super surprising. Maybe we'll do some cute notation, but then we'll do some examples, and I expect that those examples will be a little bit different from the examples that you worked in your Calculus 1 course. So let's start though with a derivative definition. So what's our definition? Well, what we're going to do is first define, as we did with continuity, we're going to define the definition of differentiability at a point. So we're going to have some function f from some domain D to the real numbers. A is going to be some element of D. And we're going to furthermore assume that D contains an A coin. So such that D contains an A coin. And this is an important point. We are not, when we talk about differentiability, even though we talk about differentiability at a point, it is not a point property. It is a local property. It talks about what's happening to the function in some, the technical word is often used as neighborhood, although we're calling this an A coin. So in some coin around A, we want to know what's happening locally to the function, how it is changing near the point A. So it's not good enough just to have A be some point in D. So for example, if my D consisted of some interval and then some isolated point A, this is no good. Okay, so we don't want this situation to be considered because it's not really clear how to talk about how the function changes near A. There's no input points near A. Okay, so that's the first bit. We have to have an A coin in the domain. Okay, fine. Next, we're going to define something that you've seen before called the difference quotient. So the difference quotient, another F, difference quotient, very long word or words, of F, and we'll either say at A, or if we want to be very verbose, we'll say based at A. So this is actually going to be a new function. Okay, so is the function, and we'll denote it dq. The sub A tells me where it's based, F. Okay, so difference quotient of F. This is going to be some function defined on D, but not at A itself. Okay, and you'll see why in a moment. The output is still the real numbers. And it'll be defined by, well, if I take dqaf of x, so x here is some non-A element of D, this is simply going to be the difference between f of x and f of A divided by x minus A. And of course, this is a slope. Okay, so if we were graphing and I had maybe some A here and I had some X there, okay, maybe my curve is going to go through A comma F of A, and X is going to go through X comma F of X. Now I don't know what the graph looks like, but I can ask, what is the slope of the line segment that goes between A comma F of A and X comma F of X? All right, and the slope is exactly equal to the difference quotient of F based at A evaluated at X. And the idea is, of course, I can change this X. So maybe I move my X over here. So here could be like a little Y. And maybe the Y is there, or the F of Y is that height. And that might actually give me something, right? That'll give me a different slope. Okay, so maybe my actual graph, right, went something like this. Okay, so at different points, right, I can get these different slopes. And this difference quotient is going to measure that slope along the way. And you can see, right, why this is a slope. F of x minus f of a, that is your rise. And x minus a, that is your so-called run. Okay, so it's just a rise over run formula. Fine. So what then is the derivative? So, well, we're going to say that the function f is differentiable, okay, it has the ability to be differentiated. So it is differentiable at A, so just at this specific point A, with derivative, okay, and then here the notation is something you'll not be surprised by, f prime of A. If, okay, well, we'll phrase this in two ways, okay? We'll use our coin language, and then we'll use the formulaic language, which at this point probably is the easier way, but let's be consistent. So if every, okay, so f prime of A, that's what we expect the derivative to be, so I'm going to look at an f prime of A coin, and if it contains the DQAF image of a punctured A coin. Okay, so that's probably just jumping the shark here with using this A coin language, but when we translate it, you'll see what it means. So i.e., okay, so we've actually already seen before what it means if I have some function, okay, so if I maybe just call this G for a moment, where I knew that every G coin contained the, well, okay, that was supposed to be like or sorry, this would be a limit L. So if every L coin contained, and here to be my G, the G image of a punctured A coin. Okay, so let's write that down. So if every L coin contains the G image of a punctured A coin. So go back. So what was this? Well, this is actually, if we go back to our definition of functional limits, right? We said that the A limit of f equals L if every L coin contains the f image of the intersection of D and a punctured A coin. All right. Well, we don't have to worry about this intersection of D business here because we already assume that our D contains some A coin. So we can just simplify. Every L coin contains the f image of a punctured A coin. And that's precisely what we're getting here. So what this is saying is it's a limit as, okay, we're approaching A, so we can write as x approaches A, of the function, well, here it was G, in the original definition was F, here it's DQA, F, evaluated at X. Okay, and the claim is that this should equal whatever this number F prime of A is. Okay, or alternatively, right, you could say, oh, well, this is equal to the limit, and this is what you probably remember from Calc 1, f of x minus f of a over x minus a. Okay, so if the limit of this difference quotient as x approaches a exists, okay, it's equal to some number, that's what you call f prime of a. All right, and if, of course, f is differentiable for all x in D, okay, which is only going to make sense the way we've written things if D contains an X coin for every X, which tells you that we're only looking right now at open sets. Now, there's a way that we can extend this in certain instances to closed sets, which we'll see in a future video. But for now, we're only going to be looking at open sets. Okay, so then we say f is differentiable on D. All right, so in the next video, we're going to do some examples and non-examples of differentiability, and then we'll do some properties in a few videos after that. All right, we'll see you next time.